Okay, in this video we will discuss another example which is given in this following form. Okay, so what's been asked? Okay, so now we have a parameter. Okay, is a control parameter sort of thing, I don't know. Okay, now I think they are going to introduce some borderline case. So show that the linearized system incorrectly predicts that the origin is a center. Okay, so maybe we could expect that by using linearization technique we'll end up identifying the fixed point as a center, okay, irrespective of any value of a. The actual fact is, if a is negative it's a stable spiral and a is positive it's an unstable spiral. Okay, so it's like, so if we linearize it, it will show that it doesn't depend on a, okay, and also it is center, which is one of the borderline case. But actually we could, I mean, the influence of a matters in this system, so that's what we have to show. Okay, let's see, first let's identify the fixed point. So it has only one fixed point, which is the origin. Okay, so there aren't any other fixed point, so the fixed point is 0, 0. Okay, now let's identify the Jacobian matrix near this fixed point, and that will provide us this matrix A. Okay, and the trace for this matrix is 0 and the determinant is 1, which is a positive, so therefore we could easily identify that it's a center. Okay, so it's a center, which means it's well, that's one borderline case, and we don't see any dependence of a here. Okay, so it doesn't matter whatever the a value is, it is always going to be the center. So that's what we have obtained from our linearization technique. Okay, but is it really a center? Is it not a stable spiral or unstable spiral? Okay, let's see. In order to analyze it further, what we are going to do is, instead of treating this system in the Cartesian coordinate, we are going to treat this by converting into a different coordinate system, which is a polar coordinate system. Okay, so we know how to convert the Cartesian to polar, where the place of x we will assume r cos theta, in the place of y we will assume r sin theta. Now the state variables are not x and y, they are r and theta. Okay, so which means I have to write this equation such that r dot is equal to a function of r and theta, and theta dot is equal to a function of r and theta, some other function of r and theta. Okay, so we need to convert that. Okay, I will leave that conversion as an exercise. Okay, and once you do those conversion, okay, you will end up with an equation which is in this form, a very simple form. Okay, so in some coordinate this equation looks very complicated, but in some other coordinates it will be very elegant and simple. Okay, I mean, actually the author of this book, what he has done is he started with this one, okay, an elegant equation, and then he converted to this one. Okay, he converted into a Cartesian coordinate just to show, just to illustrate this point. Okay, fine. Okay, so now let's see this one. From this one, what we can say is, so one more thing is, it's an uncoupled system. So r is varying in a different fashion and theta is varying in a different fashion. okay, and from this one we could also identify the fixed point. So there is only one point when r dot will vanish, which is r is equal to 0. Okay, at that point it doesn't matter even theta is not vanishing. Okay, still at that point it will be even though theta dot theta is varying, it's going to remain at that particular point, which is 0 comma 0 in the Cartesian coordinate, right? Okay, so now if this is going to be the system, okay, now how can I understand? So in the polar coordinate, what can I say? At some point, okay, at some point, let's say right now let's forget about these curves. Let's say at some point, okay, this point, at that point r is some positive value, okay, theta dot is always going to be a constant and a positive constant. So what do we mean by positive constant? It means it's going to have a rotation in anti-clockwise direction. Okay, so that's what it means. So irrespective of what my r value is, theta is going to keep on changing, and it's keep on changing in only one direction. So that's what theta dot is equal to 1 means. Okay, and this r, how r is going to change? R is going to change depends on a value. Okay, so if a is, let's say if a is negative, okay, then because r is going to have only a positive value, so r dot will then be a negative. So r will diminish if a is negative. Okay, so that's what we observe. So at this point theta dot makes the system to rotate in counterclockwise direction, but r is keep on decreasing. So finally we have got a stable spiral. Sorry, yeah, it's a stable spiral. Okay, when a is 0, okay, at that time there is no change in r. Okay, r dot is 0, so there is no change in r, but theta dot will keep on varying. So at that time when a is equal to 0, we will get center. Okay, we will get centers. And when a is positive, then r will keep on increasing. At that time we will be observing an unstable spiral. Okay, so yeah, we were able to identify, now we know the dependence of a, or the dependence of this non-linear term, in order to classify the fixed points, particularly if it falls under the borderline cases. Okay, and we have also learned one more trick, that so in order to classify, the technique which we could use is change the coordinate system, so that in some coordinate system it will be in an elegant form. Okay, so that we could attack the problem easily. Okay, thank you.